Hi everyone. So just another update on my investigation regarding using a proper driver or keeping the stock optocoupler. This was started because of questions that were forwarded to me about the possibility to improve this KEKK K100 respect to the stock version. So this is what I did. If you haven't seen the previous video, I suggest you do, so you get an idea of what the project is, or let's say investigation argument. So what I did is I initially designed this small driver board which has a MCP driver, and it's a 1406 because it's inverting, and I talk about that in the other video. But by having done a quick project, oops, there's a sticker here. I forgot to shield, or rather I did, but when you edit stuff in KiCad, because I use often KiCad for the filling, when you modify anything, the filling disappears, so you have to remember to go up and reset it. And I must have done something and forgot, and so I had these produced, and there is no shielding on the back, and the mask on the front is also the shielding mask is not there. So I went and did a revision 2, which is this one here, and as you can see on the back, you have the whole back is plated, and the 3 vias there are present. This is all ground. And on this side you have also some ground masking here and around the driver to try and mitigate any ringing. Yeah, so you'd see it, maybe this way is better. Okay. So the driver is here, then there is the 2 decoupling capacitors by design. Let me see if I can find a decent pointer. Okay. Here. I added here in this case it's a pull-up on the input. Then I moved it here for ease of use because the input is actually near there. I will show you later. And the larger decoupling cap is here with the input diode here, and basically, yeah, that's the mod. It's a small board. I did it in order the dimensions are so that it fits in the area here. So you can stick it on top with some double-sided tape, maybe I used the thick one, so you can stick it over the areas here where the MCU is, the original MCU here is. You can see it over here, so you have like 2 flat areas here and there where you can place it and remove the optocoupler. So all you have to do is that, and the wires, the connections are very short. Here on the left is the positive input, which you can get from the plus side here. You scrape a little part or just use the solders on the corner, and then just so bring the short wire there. Then you have the ground, which is behind here. It's very short too, because you can take it from the output here. And then you have the trigger. This is the trigger input, which is very, very short because it comes directly from the opto pad, which is very easy. You just wire it here and it brings the input to the opto driver. Then you can see this little pull-up resistor. I put this here because as this is an inverting driver, meaning that the signal is active low and then it triggers the output. If by any chance you unplug or there is a voltage oscillation on the input side, of course there's a decoupling cap, so it shouldn't happen, but it will maintain the input high as long as it can, so that this won't trigger inadvertently the FETs. It's not obligatory, but I suggest you add this. You can put a 5K, a 10K. It's not really important. It's just some pull-up resistor in that range to, I think this is a 4.7 K, just to keep the input high if by any chance the MCU is left floating or something, or even, for example, this wire breaks off, this can start oscillating because, you know, it's a high impedance input, so you should have some pull-up here. If you use the other MCP, of course, which is non-inverting, it's the opposite. You need a pull down. But in this case, these devices here, these spot welders, they have a negative active trigger signal on the output of the MCU. So that's how they drive the output. And in the opto, the negative side, one side of the opto is connected to plus, the other side is connected to the MCU, so when it goes down, it sinks the current. That's because sinking is usually preferred respect to driving high. That also depends on how the MCU is configured, because we're talking about the MCU side, not the output of the FET side. This is it's a push-pull FET, so it's very, very powerful. Now, I did some tests, and with it wired like this, if you can see here, just to finish the description, the output, which are these two pins here, as I didn't have any small 1/8 watt resistors or SMD things values, I used two 33 ohms connected to the same output, and I just wired them directly here to the legs, as if I wired them to the pad would lift because it's a small pad. So it's good for a piece of wire, but if you put in these thick-legged resistors, it's very easy to lift them. So I just wired them directly here. The pad is still underneath here, but it's not used. I just wired them here. So these outputs, one resistor goes to one bank of FETs, which is these 3 FETs, and then the other bank is on the back, which is covered now, but it's on this side. I could maybe show you later. And the wire reaches here because this is the common gate trace, and I cut it so that I isolated these other 3 FETs on the other side because they're all in parallel. And I soldered this wire here. It's a silicone wire, coated wire, so it goes under here. It follows the same trace and then just reaches its resistor. I used a rather high value because with lower values you really get a lot of ringing. And so let's say usually you have, on these kind of FETs, you usually have a 30 ohm resistor per gate. You can go down to 10, but you know, that's the ballpark area, 20 to 30, depending on the gate capacitance. And you have 3 of them here, so you would have, let's say the correct value would be around 15 to 18 ohms. I tried an 18 ohms. I was getting a little bit of ring, so I just said, okay, I had these and I tried these, and well, they turned out, it didn't explode, so nothing shorted. So I'm sticking with these 30-ish ohms resistors. So 3 in parallel and 3 in parallel on the back. Then you have what I added is a TVS diode. This is not super powerful, but I added it in just in case of for additional security. There's one here and there's one also on the back. So there are 2 TVS diodes for each of the 3 FETs. This is a 20. Let's say the conduction is around 22 volts, 24 volts. So yeah, these are break down at 40. So you know, we're in the, let's say, safe area. Then what else? I moved the positive side of the output directly on the connector here, because it's silly to have a let's say a bus here when you can directly get the plus from the connector, which is much better for losses. You decrease the losses, you increase the peak current, but it can handle it. It's not a lot. So this is the configuration I used for testing. And well, I did some tests, and I tried few dozen wells, maybe even over 100. I don't remember because I did them, and I used AWG, the original stock AWG 10 cables. So these are the ones that came with the default, let's say, offer. Then I used the same cables because my point was for comparison to a stock K100. This one hasn't been modded in any case. However, this is the revision, second revision, which has the decoupling trace, which goes all the way to the opto here. So in this board, you really don't need to mod anything for the decoupling side. I didn't even change the pull down resistor here, which is rather high. I didn't check the value of this one though, but the original one was several kilo ohms. I put a 1K, and that increased the off time, which is better to not overheat the FETs. These are all in parallel. Everything is stock. So I just used this with the same battery, same AWG 10 cables, which are, I think, aluminum core, because I use the same types on purpose. And I just did some, let's say, tests. And okay, gate time, of course, the rise time here is much quicker. I will try to put some graphics overlay to show you the differences between the two. Here we are, of course, in the, let's say, of course, microsecond range. It's a little bit slower because this goes nanosecond range, but due to the increased resistances here, the gate charging is is a little bit slower. So that's normal, and that was on purpose. I did this to prevent the ringing in certain situations, but what I found out is that the off time is what is actually destroying the FETs. So with the driver board and even these, let's say, higher resistances in series with the gates, the off time is also very, very significant, and you can get transient voltages way above 30 volts. And I've tried separating the cables, isolating them, also on the battery side here, separating them. I did several, let's say, morphological modifications, but the transient on the off time was always the same. And the thing is that on this side, with this default spot welder, you can see it. It's very, very limited, but it's very, very limited, and that's because this opto does not pull down the gates. It's all reliant on the resistance here, so the off time is very slow. And to be honest, I'm not sure which is more dangerous, having a very slow off time or having a very fast off time but a very high transient voltage, a very high back EMF, which is what's happening in this case. And you can actually see the TVS diode intervening and clamping it at around 24 volts and turning on and off. And I will show you this on screen to show you the difference between the stock version behavior and the modded version with the driver board. I think you definitely need to add TVS diodes on the modded board if you want to go ahead and increase the off speed, because it's very easy that those peaks, let's say, overcome the reverse voltage limit of these drain source junction, and that's not good. Then you will get a big explosion, or small, it depends which one. Usually when this happens, it's always one of the FETs that is failing first and getting all the current. But if they're well matched, more of them will fail. So if you happen to diagnose a failure in this case, and you have shorted FETs, if more FETs shorted at the same time, it means they were pretty matched, but it also means that the transient was very long, the reverse transient. So that was, let's say, exposing more than one junction to breakdown. As I said in my last video, I had to replace 4 of these because 3 were destroyed, 1 was marginal, and so I just bought a new batch. I have about 15 of them now, so yeah, I have some material to change with, to play with, and I thought that I would be destroying these pretty quickly, but until now I reached even 20 milliseconds of pulses, and well, apparently they're resisting and they don't even get so warm. And that's one of the differences I can tell by these two different setups. This one actually gets warmer than this one on the same settings. The firmware is actually slightly different. The concept is the same. This is always double pulse. They both behave the same way. But when you turn this newer revision on, the default value is, I think, like 0 first pulse, and then 30 milliseconds delay, and then some milliseconds second pulse. While here you have a longer first pulse, a delay, and then a shorter first pulse, which is kind of weird because it should be the opposite. Usually you have a kind of shorter first pulse to clean the area a little bit, and then preheat it, and then give us a second pulse to widen the weld. I mean, there are different theories on this, but okay, concept is that the two firmwares are not exactly the same. The timing is the same, everything is the same, the way they behave is also the same on the low voltage warning, but they just are, let's say, initialized differently. I think they did it on purpose, so you start with a single weld so people don't maybe mess around incorrectly and just use a second weld time for a single spot weld. I don't know. Anyhow, the concept is here that what we should take away from these tests, and I will keep on showing the difference between the two, let's say, TVS events. And now these were taken between the drain source here. So I just simply put my scope between the negative and the drain side, so the source and the drain, just to see what comes across the drain source as peak voltage. The gate input, well, that's pretty easy, not much changes, because if you check the output of the MCP, it's very fast. Checking instead here I soldered this little wire here so I could put my probe on the gate output. This is on the second batch of gates. They're the same, so pretty much. The output here, of course, is slower. It's in the microsecond range, but it's I would say that it's okay. It's pretty stable. I found no major ringing on that end. Where I found it is, as I said, on the off time. And that's when you get the reverse voltage transient, and that's the problem. And the only way to mitigate it is to slow the off time. And on a driver like this, the two outputs are actually usually used together, because one pulls it high and the other one pulls it low. If you see the schematic, it could be possible to separate them, meaning that you have one side which is going through a 30 ohm resistor, for example, to turn it on, and then the turn off side is actually going through for example, a slower 100 ohm resistor. So it slows the discharge down a lot, slowing the transient. But what does this then do? It then creates problems for the FETs that are not turning off quick enough. And yeah, you don't want strange behaviors and avalanching, or any, let's say, periods where the gate is discharging but is not yet fully discharged, and that then starts ringing. That's how you destroy, again, a FET. So it's important to have a fast off time. However, if it's so fast that the gates are happy when they're off, but they get destroyed by the reverse voltage, the transient voltage, then you have another issue and you need to clamp that. And the only way to do that is to put an external TVS diode. So for those who are wondering and asking me, why not add TVS diodes on these boards? Well, yes, why not? We should. However, on this stock board, if you're not modifying and let's say using it as it is, and this is, by the way, the 6 FET version, it's not the 12 FET. I am, I don't know, I'm not too keen on buying, on having 12 FETs on these boards driven by one single poor little junction, NP junction here. It's not really the best thing. You're gonna slow the on time and off time. You're gonna have to, because I mean you're doubling the gate capacitance by putting double the FETs. So that's gonna create even more issues if you're trying to overdrive it, and that will also not be a good thing. Though you won't have major transient voltage peaks here because of such a slow time. You get them, but they're very limited. It's in the under 10 volts or something like that. Instead, when you have the driver board like this on, then you're going to see peaks that, well, from what I could see with the little scope, which I was using that Zoe, you can get over 30 volts easily. So that's near the destruction of these gates. That's why of these junctions. That's why I think that with my original board without the TVS diode on, because I tested these the first time. I didn't put any TVS diodes, and it instantly on the second weld, I think, something like that, it just blew all the FETs up, nearly all, and that was a big signal of something that was majorly wrong. I first was worried more about the shielding and ringing of the board, but I sincerely think that it was a transient event that destroyed the drains that went over the reverse voltage of these FETs. So anyhow, here is the another board without the larger cap on yet. I simply made these boards without the components, so they're pretty cheap. I think I paid around €4, 4 or 5, with shipping 4.5, something like that. And I just soldered on the components, and I prepared a second one because I thought better have 2 ready. But this one is behaving nicely, and I haven't had any problems apart from that transient voltage, that kind of back EMF that is formed probably between these 2 bars. I was trying to let's say remove them to try and use a braid here, though I don't think that really makes a big difference, because I soldered these a little bit better here when I was using hot air, so the contact here is better than the original, which I suggest if you can do, or even just remove them and place a maybe a flat a rectangular profile bar here, or if you have copper, even better, because these are bronze. It's an alloy, so okay, anyhow, that's basically the big takeaway from all these tests. I was trying to, let's say, see these 2 perform side by side with the same settings, and it was a little bit hard. What I can definitely say is that when this triggers, it definitely gives you that very, very discrete pulse, which you can feel, because it's fast, so you can feel the let's say the field and the current pulsing through. It gives that jump on the battery leads. It's more aggressive, with this driver board, but that's to be expected. And what I was doing is I was trying to, let's say, spot weld two sides. So this is a 0.1 millimeter strip, so it's pretty thin. This is a point, actually it's in the middle around 0.13, 0.14. It's not a definite value, depends. So let's call it 0.13. And I sandwiched them, and I was trying with the same settings to spot weld these with one pulse. And I reached around 18 to 20 milliseconds. I had like a first pulse on here, like 4 milliseconds, pretty short, with a 5 millisecond delay. And then I was working on the second pulse, ranging from 10 to 8 milliseconds all the way to 20. And this was actually, it managed to actually solder, but only on the surface side, on the second layer. So the first layer is definitely, well, it solders, these both solder spot weld the first layer very easily. I've done it also on thicker, on between 2.13 or whatever surfaces. I did a lot of welds here, putting them one on top of the other, and they are welding pretty well with even second pulses like 12 milliseconds. They are more or less equivalent, though I think that this one is, as I said, more aggressive, and probably can reach better performance if you go ahead and increase the size of the electrodes. I have also recovered AWG8 electrodes with replaceable tips. I haven't tried these yet because I wanted to try easily with both spot welders with the same type of cables. These are actually the same, and otherwise I would have to unscrew and screw these both on. And instead I wanted to try them very quickly just by unplugging and plugging the battery. And these are thicker, and the length is more or less the same. The material, I think, is always aluminum core, because I doubt that these are using pure copper. But being thicker and having the tips which are, let's say, rounded already, and they're not flat, because the original tips which they give you, which are like these are usually flat. And what I do is I slightly round them. I've spoken about this in my other videos, so again, if you want to dive deeper in the subject, feel free to check out the frequently asked questions video, or the latest video on the spot welder list. I round them up so you don't have just a little surface area when you're contacting them. That's because when you weld, you're usually holding the electrodes at an angle, you know? You're holding them like this. You're not holding them like this. And this makes only the edges touch, and the edge is a very small area. So there will be a lot of current going through a small area, and that's going to easily weld, right? But you're going to get a small surface weld. So when you rip them off, if you want to try, you can rip the metal, the strip off, and it's easier to rip off because a very small surface has been welded, and you get a hole. But if you try welding with a rounded point, you're going to need a good amount of current, because you're going to have a larger surface contact area. But when you do weld, that's going to be harder to rip off. It will strip off a piece of strip. Anyhow, that was just a little heads up, because the original are, well, I've filed these already. I'm sorry, maybe you can hear this, see this, yeah, here. I filed these already a little bit. These are a little bit flatter, but if you can see the edges, they have been filed, so that they are very similar when I do the tests. So I might do another couple of tests with these on this one and on the other one, and see what kind of, let's say, transient voltage I get event, and see if these are actually giving you better performance. I mean, theoretically, yes, if they're thicker, more current can go through. As long as the FETs can support that peak current, you should be okay. So we'll see. That's where I'm at now, and the big thing is the transient, the TVS event on the fast offside. So yeah, if you do go ahead, and the people who have done the mod even by themselves, that's what I suggest. And please consider the transient voltage on the off time, and that is always proportional to the speed of the off time, because we're talking about inductive loads. So the faster the field collapses, the higher reverse voltage. The more brief, it's inversely proportional to the time. So the briefer the event, the higher the peak. And that's exactly what you get with a fast switching driver, in opposite to a simple opto, which just drives the FET when you're turning it on. So you're pushing the FET on with the gates, but when you're turning it off, this doesn't really do anything. Everything relies on this little resistance here. I don't know if you can see it. This second one here on the left. That resistor there is what is discharging the FETs. And to be honest, it's really slow. I think you should, if you want to stay on the safe side, modify this, put a 1 kilo ohm at least on this side, or at most, let's say, because you want to go down, and that will cut the off time, and you won't have still enormous, let's say, peaks, because you're still pretty slow, but you're reducing the transient voltage event. On this side, the alternative is to split the outputs here, which are actually split because these two pins are separate, and use one to pull the gate up and use the other one to pull it down. They are able to do that, even though everybody, of course, uses them connected on the output, but I don't know, it's possible. Of course, you have to always use then a pull up and a pull down for safety reasons, so this board has to be reworked. I don't know, if I have time, I might think about it, but let's say that if you want to, let's say if you're handy and like to, let's say, do your own tests, you can, I can also give the Gerber file or the project or whatever and link it to Google Drive or whatever, and so you can download it and have it produced by yourself. I mean, it's very cheap, or even the KEKK project, so you can modify it. As I said, it's really a simple design, not hard to reproduce. It's just I think that I will probably keep it at this revision with the output like this, or if I really want to do the test, I can just simply break the tracks here and use the 2 pins output and put 2 resistors, a pull up and pull down externally. I know it will be uglier, but if you can, for testing reasons, you can do it. I have the board, so why not? I don't know, I will see. I will try with those bigger electrodes and see if I can get better performance instead of these AWG10 with these core. As I said, I moved this here. I suggest everyone does the same. You could theoretically, and I've spoken about this also to others, if you don't use this, if you don't have an XT60 connector, you can also, and you're using, just simple screw-on terminals, you can simply have a direct terminal coming from the positive of your battery, and then just use a thin wire to the board, just to power the board, because the current is going through the positive then the FETs. The board is really just, this is just really here for losses, let's say, or just to power the electronics and for handy, ease of use, because you have an input and an output. But you can really just, like the electrics and everything, you can just unscrew this, put the two terminals together, or if you want to change the whole cable and put a AWG, I don't know, 8 or even 6, and feed a longer one from your battery, and then just from your battery put a normal like thin cable or thin wire just to power. You can solder it on here or something, and just to power the FET, it will work the same. You're just separating the high current path from the positive side away from the board, which isn't bad. I mean, in this case, I couldn't do it because I'm using an XT60 connector and I didn't want to have additional cables. I mean, I have an adapter cable where I can screw the screw-on terminals and then have an XT60 connector. Actually, I have two of them in parallel. But I mean, I wanted to try it as stock as possible, let's say, and as this is very short, the positive side going from here to here, I mean, you're not really gonna experience a lot of loss here. This is the side where you're gonna be experiencing the drop because of the internal resistance naturally of the FETs and the traces. So yeah, also the fact that I used 3 FETs on the back and 3 FETs on the front, the current is more distributed, passing through the track on the back and on the front. It's true that they did these mesh here with all the vias to try to keep the two surfaces as mostly in contact as possible. But yeah, by doing this, you're kind of splitting the two pathways, and yeah, they're bolted on this side, and on this side it's soldered. I was also thinking of putting a screw-on terminal here without anything, just to bolt these two surfaces together. But I don't know, I decided to leave it like this. Maybe better to avoid ground loops, I don't know. It's not going to be a major issue in this case anyhow. So that's basically what I've been thinking about and testing. I hope you enjoyed this, and maybe you can take something away from this too, because when you're experimenting, you always learn something, even if you have a lot of baggage, let's say, of experience, because these kinds of events, these, let's say, I call them like single shot slow speed transient events. You're not working with a switching power supply when you're in the hundreds of kilohertz of frequency. You're not working with lower current, like, of course, again, in power supplies. Here you're dumping a 400 amp, 500, 600, or even more load current in a transient, which is just a few milliseconds. So that's gonna cause big transient events. And yep, we've all seen what the issues here are. And yeah, as I said, if it's the first time you're watching this, feel free to visit the spot welder list. There is a video, it's a playlist where you have all of the spot welders and all of my videos, and the frequently asked questions ones where I dive more on the techniques. And yeah, people are always asking which is the better one, which is the worst one. At the moment, from my experience and the fact that these are the ones that I have had, let's say, the possibility to test, I would say you could get this basic one with the 6 FETs. The kit, I think this one cost me about 35 euros, because it came with the cables and the plastic cover, the plexiglass cover, which I got directly from the I think their AliExpress site, or the KEKK. And the what I asked, yeah, they sent me another display here, because yeah, I was using the hot air and I removed them and put it back, and I forgot to remove this while I was blowing hot air here, and it kind of like, where is it here? It got slightly deformed on this edge here. I don't know if you can see it. Yeah, you see, got the heat here. Well, it works fine, but it's kind of ugly. So I asked the guy, that the seller, and man, they sent me one for free when I ordered this one. So yeah, they can help. I said, well, I'm doing some reviews. I did actually reach out and ask them if they would send me a sample. I was kind of ignored, but yeah, it's expected. This is a stock. I didn't solder anything on this side. I just kept it. I wanted to keep it as it is. I didn't even put the plexiglass cover on. So between the two, which one performs better? As I said, using the stock cables, this one certainly, I mean, on the trigger side, you can feel that this one is triggering very quickly. And I think this one does deliver more energy, because the fact is that even if I did a few dozen wells trying to reproduce one and unplugging and putting on the other, you're never welding the same way, because the pressure you're applying is different, the surface is slightly different, the terminals are not really contacting the same way. It's very hard. I don't know. I think that on generally speaking, you can definitely see that this one is performing faster, and I think it does weld better, because not the spark, but the heat that is generated, the cables do heat. You can feel them get warm, but the FETs do not. The temperature here is pretty stable, even if I haven't done, like, for example, 50 welds with this one and 50 welds with this one. I usually do like a few welds on one end and check, and I then check the scope, so some time goes through between one weld and another, and it has some time to cool down. But I did notice that when I did a few welds in succession in this one, I could feel these getting warm, and I could see the temperature on the reported Celsius display increasing a degree or two, while on this end it never really changed. To change it, I actually have to put my finger on the thermistor here. It's this little component, and then I would see it change, because I thought, wow, maybe it's defective, and no, it does change and immediately goes down to the same value again. It may also be because I don't have any FETs on this side. They are exactly though on the other end. So they are exactly on the other side. So there is the board in between. So there's a sandwich that may contribute, of course, to the latency. But after a while, it should heat up anyhow. And if you put your finger on, you can feel, I could feel that these were warmer respect to these, even on the other side. I added this protection, but it's very easy to, just flip over, and I would put my finger here, and yeah. I added also capped on tape, because this one doesn't have any protection on the underside, and you never know on metal surface. Always be careful, because you're shorting out your load battery there, and that's big. If you have a battery or a cap bank, it can be a rather big event. Okay, so again, it's about 40 minutes. I've been talking a lot. That's let's say that's what I've been able to take of this, and I will be doing further tests. Maybe I will show you more in depth, let's say, graphs, but I think the ones that I will show you here will be enough. And in the meantime, if you like my content, always feel free to subscribe or like or whatever. I should be saying this always in the beginning. I never do, because I'm more concentrated on delivering the content than the other stuff. As usual, if you have any comments, you can just comment down, and I always try to reply as best as I can to everybody's questions. Again, many of the questions have been already replied to in the previous videos, so please feel free to check out the frequently asked questions video. It's in my spot welder playlist, and or all the other videos, because I often reiterate myself, as I see that people are asking very often those similar questions. I mean, I understand one arrives and of course asks immediately, so and not going through all of the videos, because it can be a long view, because my videos are usually a little bit too long. For the average content, they should be like under, I think around half an hour would be good, but depends on what you need to show. So okay, have a good one, everybody, and see you soon.